Welcome back, everybody. In lecture 19, we're going to be talking about linear approximations and differentials. So we briefly talked about linear approximations back in lecture 9. This was using the tangent line to get a rough estimate of what the value of a function would be near a particular x value. So this is exactly what the linear approximations are going to be here, and we're going to give a name to them. So let's go over the idea first. So suppose we have the differentiable function graphed below. So I'm going to graph a function below. It'll be this function right here. So here's my x and y axis. And then here's the function. We'll call this f of x. And I'm going to pick a particular point right here. I'm going to call it A. So right here, at this spot, this is going to be f of A. And what I'm going to do from here now is I'm going to draw the tangent line to the curve at A. So it looks something like this. So it just touches the spot right here where x equals A, and then the tangent line does something like this. So notice for x values near x equals A, the tangent line, so the pink line, does a fairly good job approximating the value of f of x. And here's what I mean by that. So let's take some very small distance away from A. Let's say this one right here is going to be A plus h. So right here above it, at this spot, this will be f of A plus h. So notice from here to here, we have this change in the tangent line value. It's right here. And their gap right now, from there to there, is the estimate, is the error between the actual value of f of x and then what the tangent line is. So if you go a very small distance, the pink line does a pretty good job of still approximating like what the value of f of x is going to be. However, let's take this to be b. Let's take that x value to be b. And I'm going to continue my tangent line, and I'm going to go even more here, just so I can get over there. So now I've really exaggerated this, but here is the spot on the tangent line. It's down here. Let me draw that a little better. So here's the tangent line at b, and here's the actual value of b here. This is a very large distance here. So now that we're this far away from A, this is a very poor approximation of what the original graph is doing. So we probably wouldn't want to use the tangent line too far away from the original A value where we were tangent to. Okay? So this is what I mean by if you're near the x value where the tangent line is taken, then the tangent line is a good approximation for the graph. Okay, let's look at a definition for this idea. So the definition is, given a differentiable function f of x, its linearization at x equals A is, so linearization is the thing being defined here, we say it is L of x equals f of A plus f prime of A times x minus A. And we say that f of x is approximately f of A plus f prime of A x minus A. So this linearization, this L of x, is exactly this pink tangent line that I drew. So approximately f of x is going to be this value right here. let's look at an example, like an actual numerical example. So here's my example. We're going to find the linearization of f of x equals the square root of x at x equals 16, and we're going to use this to approximate the square root of 16.1. OK, so let's go ahead and write down everything I need. So let me change colors here. First things first, I'm going to write down what the original f of x is. So in this case, f of x is the square root of x, which is the same thing as x to the 1/2 power. In the formula for the linearization, I'm also going to need the derivative. So I'm going to write that down. So the derivative of this is just a power rule. So bring the 1/2 down, and we get x to the negative 1/2 power. I can rewrite that by saying 1 over 2 radical x. So this is my derivative. OK, let's start building the linearization. So it says that L of x is equal to f of a. And this time, the a they gave me is right there. It's 16. So I have f of 16 plus f prime of 16 times x minus, and then a is 16. All right, let's go ahead and calculate what some of these are. So this is L of x is f of 16. I plug in 16 into the original, and I get the square root of 16 is 4, plus I'm going to plug 16 into the derivative, and I'm going to get 1 over 2 root 16. That's going to be 1 over 8 times x minus 1 over, or x minus 16. So this is my linearization. The second part of the problem asks me to use this to approximate 16.1. So it's very difficult to calculate the square root of 16.1 by hand, but we have this linear thing now that'll at least approximate it. So let's do that. So we're going to say 16.1, it's approximately 4 plus 1 over 8. And now I want 16.1, so that's the x I'm plugging in. So 16.1 minus 16. So this is equal to 4 plus 0.10 over 8, which is equal to, and this is equal to, let me see, I have a decimal here, 4.0125. So this is an approximation for this actual value. Let me draw what we just did. So down here, I'm going to write, what did we just do? OK, so let's figure that out. Let's go over here where I have all this space. I'm going to draw a graph just like this. I'm going to draw the original square root graph, which by now you should know this looks like this shape right here. Something like that. And I'm going to mark the point at 16 here. So I'll say that this is 16 for the x. So right here, you should know that this value right here, when you plug 16 in to f of x equals, let me scoot that over a little bit so it doesn't go off the screen. F of x equals root 16x. This will be 4. What we did is we took the tangent line there to approximate this value right here. So this is the square root of 16.1. Here we have this tangent line at x equals 16. And right here, just above this value of square root 16.1, this is the value that we found, this tangent line just above there. So because we're very near 16, this is close. So we see our tangent line overestimates the actual value of radical 16.1. You know that because the tangent line is above the original graph. So what actually is this? So I did this just to check my work. So if you put this into a calculator, this is approximately 4.01248. And notice just how close our approximation is. It's just barely larger than this by 10 thousandths, okay? And if we were to go and estimate things further and further away from 16, our estimate would become worse and worse because this tangent line would start to separate from the original graph. Okay, so I hope that idea of linearization made sense. In the next part of this video, we're going to be talking about some more vocabulary having to do with this situation right here of having an error between our estimation and the original graph. So I'll see you soon. All right, so now I'm going to go into differentials, and we're going to go over some much needed notation for the rest of this lecture. So here I have f of x. It's going to be some function. So I'm going to say, let f of x be a differentiable function. So I have that function pictured just over here. And I'm going to go back to my notation of saying this is a. But now when I have a change in x, I'm going to notate that differently. So let's go over here. And I'm going to say this is a plus dx. So this distance from here to here is called dx. So that's my first notation. And I'm going to label that a couple different ways. So this delta symbol here means change in. And x right here, the change in x is going to be equal to dx. So this represents a small change in the x value. So delta x or dx, they are both the exact same thing. They both represent a small change in the x direction. OK, so now if I look at this, the function right here at f of a, I'll call that y1. And then the function at a plus dx, so right above this one, we'll say this is y2. So what I'm going to do is I'm going to, again, draw my tangent line from x equal to a. So we're going to have a tangent line at a particular point. I'm going to try this blue here. OK. So that's my tangent line right here at a. And notice it's a very good estimate for the original graph for a while. And then you'll see that the tangent line starts to separate from the actual graph. So my change in y is going to be delta y. So this represents the actual change in function value. And that's just delta y is y2 minus y1. And the other way you could notate that is you could say it's f of a plus dx. So it's f of this x value right here minus f of a, the original value. So either one, they both mean the same thing. Y2 minus y1 is something we're more comfortable with seeing. But it's this distance right here. So from here to here, from one pink dot to the next one, this is change in y. It is the actual change in the function value. The last thing I want to talk about is dy. So dy, I'll put that over here. This is the differential. So dx and dy are both called the differential. Dy represents the change in the tangent line value. And this is represented by dy is f prime of x dx. And let me draw it on the picture as well. So here is the tangent line value at a. It's shared with the function value. And then here it is when you finally get over to x plus dx, or a plus dx here. It's above where the actual function value is. So from here to here, from where we started on the tangent line to where the tangent line is now, this distance is dy. And notice that that's a greater distance than the actual change in y. So the tangent line here is an overestimate. OK, so those are the 4 different notations you have to know for this section. So you have change in x and dx are the exact same thing. They are this distance here, this x distance. The other 2 are not the same. So delta y is the actual change in x, or actual change in y value here, while dy represents the change in the tangent line value. So let's use that knowledge to solve this problem. So I'm going to calculate both the change in y, the actual change in y, and the differential dy for this function right here. So actual change in y is pretty easy. This is y2 minus y1. So that's equal to, if I say that this first x value is x1, and I say this one's x2, then I have, I'm going to plug in x2 first. So I'll get e to the negative 0.5 sine of 0.5 minus, and I'll plug in 0, e to the 0 sine of 0. So this is the actual change in the function value. It's like you're doing the slope formula, pretty much. Plug in 0.5, plug in 0. You'll notice that this just reduces to this first term, because sine of 0 is 0. So we get e to the negative 0.5 sine of 0.5. I don't have a calculator, and I didn't bring one, so we're going to leave this as the answer here. That's my actual function value. Let's look at dy now. So for dy, I'm actually going to start with something else first. So we're going to review some derivative stuff. And let me switch my marker color as well. So I'm going to start with the fact that y is e to the negative x sine x. I'm going to take the derivative of both sides. So this means dy dx, so the derivative with respect to x, is equal to, and this I need to do the product rule. So leave the first one alone. The derivative of the second one is cosine x plus, I'm going to take the derivative of the first one now, which is negative, let me change it to a negative, negative e to the negative x. And I'm going to leave the second one alone this time, sine of x. So this is dy dx. So to get dy, all I'm going to do is write dy equals what I found earlier, e to the negative x cosine x, minus e to the negative x sine x. And I'm going to multiply this by dx. All right, so now to get dy, I need to plug in all my pieces of information. So this x right here is based on the original x value. So the original x value is 0. So all these x's, I need to plug in 0 for. So this is going to be e to the 0 cosine of 0 minus e to the 0 sine of 0. And finally, this dx stands for the change in x value. And it has a direction to it, too. If we went from 0 to 0.5, that means we increased. So this is positive 0.5. So maybe I should mention up here as well, delta x is x2 minus x1, just so you can have a sense of if it increased or decreased, because this could have a negative sign as well. And then if I take a look at this, again, this term is gone because sine of 0 is 0. Here I have 1 times 1 times 0.5 is just 0.5. So you might want to check if these are close, if this differential was a good estimate for the actual change in value or not. So maybe put this into a calculator, see if it's anywhere near 0.5. But this is how you find the actual change, delta y, and this is how you find the differential. my last example is over here. It's a word block. This says we can use differentials, so dy, to estimate maximum possible error. And it doesn't have to just be dy, it could be any variable. We know implicit differentiation by now, so we can take derivatives with respect to any variable. This example says, a company produces a cube-shaped object with 20 centimeters as its edge length. The manufacturing process produces an error up to 0.1 centimeters in edge length. So you're producing this object, there's some kind of error with the machine, so you could expect it to be off a little bit, somewhere up to 0.1 centimeters for each edge length. Using differentials, estimate the maximum possible error, relative error, and percent error in the volume of the object. I need to specify that, so I'm going to specify that. All right, first I'm going to generate some kind of formula. So over here I had a formula. Here I need a formula to take the derivative of. So I'm going to look at a cube, and the edge length is supposed to be 20 centimeters. However, there's an error of 0.1 centimeters, and that could be plus or minus. So we could have an error in the edge length. What's my volume formula for any cube? Well, this edge length is going to be varying a little bit based on how the machine is doing and producing that standard 20 centimeters. I'm just going to call the edge length x. And the volume formula for a cube is just going to be length times width times height, which is just x cubed. Let's take the derivative of both sides with respect to x. So this is going to be dv dx is equal to 3x squared. If I move dx to the other side, this is going to be dv, the differential of the volume, is equal to 3x squared dx. OK? So the standard cube, the starting x length is supposed to be 20. So we would expect this to be 20 if things were functioning properly. And then the change in x, the change in this, could at most be 0.1 in either direction. So we'll say it could be at most plus or minus 0.1. So it could be this. Or, I guess in the most extreme case in the other direction, this could be off in the other direction. It could be under by 0.1. It could be at 19.9. So let's just simplify this top one. So if we take this one, we have 3. 20 squared is 400 times 0.1. 0.1 times 400, I'll move the decimal over to 40, times 3 is 120 centimeters cubed. Would be our maximum possible error. And I could go the other way as well. I could be under by negative 120 centimeters. I noticed that I kind of sloped down here. So let me move that up here. Maximum possible error. And allow me to go up here. So this means, so if everything was working perfectly, our volume would sit at 20 cubed, which would be 8,000. So if you vary that around 120 centimeters at worst, this means that the volume is somewhere around, if I add 120 to that, it's going to be 8120. And if I subtract 120 from that, it's going to be 7880. And these are both centimeters cubed. So the volume of this cube is going to vary somewhere around there based on the error. How do you find relative error? All you need to do is take, so for relative error, you're just going to take dv over v. So this is going to be 120 over 8,000. So this, if I cancel these here and I divide both by 4, I get 3 over 200. So that's 0.015. So that would be the relative error. And then from here, to get the percent error, you can just make that into a percentage. So you can bump this over 2 to the right, and you get 1.5%. And again, it's the same with the other situation. If you're under by the 0.1, then I would just make these negative, and I'd have this would be negative right here. OK, so that's an example using differentials to find the maximum possible error. So you should be well equipped to go do lecture quiz 19. And until next time, I'll see you in class. Have a nice day. Bye.